But hey, looks like we can start. Welcome back, everyone. This is our last class. It's almost kind of sad. If we had just another, I'd say 48 weeks, I think we could do every single concept in the book. But we hit the main thing, so that's the important thing. Our goal is just to get through as many review questions as we can in this document. And as we go through those, the definite thing you'd want to take a look at, as well as when you're studying on your own for your final exam, definitely have this thing open. You don't necessarily want to print it out unless that's convenient, then go ahead and print it. But at least having it open, maybe on a different screen, different monitor, is going to be a big help because when you're taking the real final exam, you want to know where every single element is on this page. In fact, on the vertical matrix theorem, definitely go through it, maybe color code it. You'll get it just like in this format on the real exam. But the more you're familiar with everything on here, the easier it is to use. Second page of the handout is going to have things about linear transformations. Let's see, this one looks like a terrible theorem, but the major thing you'd want to use on this theorem is pretty much that statement right here. Let me see, yes, right to here is the major portion, and there's other good stuff all around there. Also, we have the subspace definition and the definition for a basis. So those are going to be the major things. Stuff that's not on there is stuff along the lines of spanning as a definition, or what is a basis as a definition, or excuse me, what is a dimension as a definition, that kind of stuff. But any questions, folks, before we get started? Okay, I think I should, maybe before we just start doing a whole bunch of math problems for 75 minutes straight, let's open it up to the class. Are there any questions that you'd like to go back to? Old exam questions, old homework questions, anything along those lines that folks would like to take a look at first before we get started? Looks like we have one, so let's give it a minute. Exam 3, first question, absolutely. Hello. So we're going to take a look at this one right here. Oh yeah, this is not an easy question. And on the real final exam, I'm only asking one subspace question. And it's a subspace question that you can answer pretty fast. My big hint is ask yourself if the zero vector is in that set, because that's usually the very first thing you want to take a look at. But this one's a little bit different. This one's about closure, and this makes it hard. Let's put it right here. And if we are putting in questions on this document from different sources, I'll just put a quick note. This is the first question on exam 3. Thanks for starting us off with that question there. So we have a set W consisting of vectors A, B. So this is a subset of R2. The property that the vectors obey is that the product of the entries is non-positive, so negative or zero. Show that closure of vector addition does not hold. So we're more interested in vector addition. And if we go just off this step, really all we're going to do is what they say here on the very next sentence. We have to find two vectors, u and v and w. Let's start by doing that. Let u equal and v equal. Before we start putting things in, we also want to take a look at what is the condition to actually being inside the set W. We have to obey this right here. So let's try and give a good counterexample. How about, I can't go 1, 1. That's not going to work, right? How about negative 1, 0? That might do the job for us. But before we move on, definitely do this. A is the first entry, B is the second entry. Multiply them together. Negative 1 times 0 is 0, which, true, it is less than or equal to 0. It satisfies that condition. And that tells us U is in W. Doing this check on paper is a great protection because it ensures that we really know we took a vector out of here. Now, we're trying to get a counterexample. I don't even know if this one's going to work. I'm just trying stuff. How about for a second vector? Any volunteers on what could work with this one?
0 and 10.
0, 10, awesome. Thank you, Christian. So for 0, 10, it almost feels like it shouldn't work, right? This is saying negativity, but that's not true. That's actually saying non-positivity when you take both entries and multiply them. So take 0 by 10, comes out as 0, and 0 is, these always look weird. It is true that 0 is less than or equal to 0, but that just means it's inside the set. So V is in W. So now let's see here. It says that is find specific vectors U and V in W. We just did that, so we're on the right track. And I didn't mean to scribble. That was meant to be an eraser. Now it's asking us to explain why those two vectors we chose, U and V, is not in W. In other words, the not in W means we want to show that the entries A times B, you have to negate this entire statement, and the negation of less than or equal to 0 is strictly greater than 0. So we don't even have the possibility it equals 0 any longer. Let's add these up. U plus V is going to be equal to -1, +10. And if we take the entries, U times V, add them together, we're going to get -1, +10, coming out as a -10. And this one would be less than or equal to 0. Means this one didn't work as a counterexample, but that's okay. We don't want to throw out everything. We want to keep our work and just see how could we have flipped this to come out as positive? What adjustment should we make? This one right here, let's make it a +1. Let's come down. If we did that, this becomes a +1, but that's okay. It still satisfies the condition. It's still in W when we make it a 1, 0. Now, when we do the vector additions, this is going to be a 110. Let me highlight to right here where we made the change. So we put a +1 here, and our condition checking, that's now +1. And when we do the addition of vectors, we have a +1 here. Now down below on the condition checking, that turns into a +1. This is now a +10. And that means we have satisfied our objective. That is greater than 0. And so that follows, if it's greater than 0, it did not satisfy this condition, meaning our vector U plus V is not in W. So U plus V is not in W. Well, that was kind of a wild adventure on these kinds of things. And what's tough about this problem is there are infinitely many correct answers on this. There's a lot of vectors U and V inside the set, from which you add them together and you leave the set, you break closure. So sometimes when you have to come up with a creative counterexample, I think those are kind of hard questions. So I'm not going to ask these a whole bunch of times on the real exam, but knowing how this goes will help with the subspace question that would be asked on the real final. Any questions at all, folks, with that question here? Okay. Any other questions folks would like to take a look at?
In question 14, for B and D, I'm not sure that.
Yeah, absolutely. So question 14, how about we take the whole problem? Why not? We'll just take a whole wild adventure on this thing. So this one is all about just looking towards what the dimensions are for different vector spaces. And if I can get that, there we go. I just want to say this one is from exam 3, just as a paper trail. Okay, so going down the list, if we're looking at R5, then the basis for that would be E1, E2, all the way through E5. So this one would have dimension R5 equals 5. But this one is a kind of a tricky one to deal with. This is just P. It's not like this one, P7. Let's maybe take a look at P7 to help us with that vector space. For P7, this is the space of all polynomial functions with degree at most 7. So the standard basis for this thing would be 1 t squared, t cubed, t power 4, t power 5. I really thought that would fit. So let me drop a line. T power 6, t power 7. We now have 7 elements in that set. Excuse me, 8 elements in that set. And that tells us the dimension of P7, number of vectors in a basis, and that is a basis. So it's of dimension 8, but now What's wrong with this one? Why can't we get a dimension? The trouble is, if you want to write down a basis for P, that's the space of polynomial functions of any degree. And suddenly it's become a very, very convoluted and complicated vector space. If we attempt to write a basis, it would look like this. 1t squared, t to the power of n, and it just goes like that. This is not the kind of basis we even study in linear algebra. It has infinitely many different vectors inside there, which enables you to do weird things. You can add these together and do stuff along these lines. Summation n goes from 0 to infinity of, say, t power of n over n factorial. You've got infinitely many vectors in there. You can take an infinite sum, but that thing is now e to the power of t. So you can do some very, very bizarre things in this vector space. This is essentially calculus 2 right here, saying that's the Maclaurin series for the exponential function e to the power t. But the main takeaway with P is, if you have to list infinitely many different values to get every single vector inside there, it implies right away dimension of the vector space P is infinity on this one. So that's our infinite dimensional vector space. Any questions about that so at the moment? Okay, I think this is a trickier question than it looks on face value for sure. And this problem right here is also tricky. If we want the dimension of the trivial vector space, the one vector space that contains nothing but the zero vector, what would you all say the dimension should be for this thing? Dimension 0, good call. This doesn't even have a basis. The zero vector is linearly dependent. So we say just by a definition, we take this one to be dimension 0. Now C01, well, you can think about this one in these kind of terms. These are polynomial functions, and we could restrict their domains to a closed set from 0 to 1. All the polynomial functions are continuous, and so it is a subspace of C01 in that sense. But the dimension of this thing as a subspace was already infinity. This must have dimension infinity as well. You might feel like C01 is more complicated than this thing, but they're both infinite dimensional vector spaces. They're pretty equally complicated in their own right, so that's kind of an amazing fact. So dimension of C01, all continuous functions on a closed domain, is infinity as well. And let me add a little bit more words to this one. P is a subspace of C01. The only adjustment you have to make is you would have to restrict the domain of every polynomial function to the closed set 0, 1, and then that makes it the true subspace. Well, that's a nasty question. Did that help out with going through these ideas here? Any questions or comments about others that folks would like to take a look at?
I guess do have a quick question. The final exam for spring 2022 that's posted in Moodle, if we go through that as preparation for this upcoming exam, would that be adequate preparation, or should I extend the preparation to the previous exams we've taken?
That is a really good question. And that's kind of the danger about a real exam like this one being posted. To kind of give the best answer to this question, let me tell you how I wrote this exam and how I wrote our current exam for this semester. I write all of these exams by putting together this document. I do it every single time. And I go through this document and I just take a representative sample on a chapter by chapter basis of the problems that we did actually in the class. And I cross-check those problems to see, did we do them on the homework? We did them on the homework. They make a great final exam question. But what that means is from semester to semester, I'm not necessarily always asking the same kind of questions. So although this is a great one to take a look at, its main purpose is to show you about the length and the format of a real final exam. Some of these questions I am going to ask again, but not necessarily every single one. Just for a hint on the final exam, I didn't ask that question there. I changed it out for something involving spanning when a vector is in the span of some other vectors. So I'd say this is a good one to go through, but after you take a look at that one, blank exam 1, 2, and 3s are a good one to take a look at. And beyond that, what would be a good one? Well, we're already using up these problems, but you could take another look at those, or start looking at, say, more problems on this one right here. This would be this huge file to take a look at. It's probably, you know, they are a little bit slightly different problems. I wrote this in 2015. So let me start over. I'd say, take a look at this exam to get a feel for what the real final would be. You should be able to solve those questions, but this is not necessarily the same questions on every exam. So going through the other exams, like you mentioned, will be the next best thing. And then after that, you'll have a good idea of where you want to study more. Maybe it's something about eigenvalues, eigenvectors, or maybe it's something in chapter 4. Use these notes to go to the specific area to target a section. And then just try to do some of these problems here. I do look at these problems. I change some of the, well, I change all the numbers here, but these are the kinds of questions I'm looking at first when I go to write the real final exam. But does that help out with that question there, Christian?
Yes, it does. Thank you.
Yep, absolutely. Any other questions at the moment? Okay, well, on our review document, we're going to go down to this next question. But if there's other things that come up, say maybe something on exam 2, exam 1, something on an old homework assignment that you'd like to take a look at, don't hesitate to interject. Even if I'm in the middle of a problem, you could put something in the chat and I'll just leave the chat open and I'll make sure I get to it. But here's our next question of the day. This one is a true-false question. So I'm going to leave this up to you guys. I don't think I asked a question like this when I wrote the real final exam. It's still helpful for studying because we're going to look at these kinds of ideas. But I'll leave it up to you. Should we go to this question or should we skip it? Let's do it. Awesome. So let's take a look. The 4x6 matrix has 3 pivot columns. When I read that much, and they didn't give me the matrix, the best strategy is to actually just draw it out. A equals, and sorry about this document, I didn't format it for any space, so I'm just actually entering in the space there. Sorry if you're working on a PDF document. So this is going to be 4 rows. My solid dots here are just going to represent any number, but they'll have to obey the fact that there's 3 pivots. There are 6 columns. This dot pattern just about makes me dizzy to look at, but here they are. 4x6. I should have made that a little bit smaller, but here's our matrix of size 4x6. There are 3 pivot columns. I have no idea where they would be, but I'll just put them in like this. I should recalibrate this pencil. There we go. So there would be the pivot columns, and they're asking us the question, well, several questions, true or false on each. Does the matrix equation AX equal B have a solution for every single vector B in R4? What would y'all say to that one, true or false? I absolutely agree. This is false right away. What's the theorem? Not the invertible matrix theorem. This is non-square. So we go to the next best thing. We want to use theorem for. Notice that that's the very first theorem you're going to see on your exam. After that, it's the invertible matrix theorem. But this question right here is relative to this statement. This would have a solution for every possible B, provided, let's take a look, A has a pivot position in every row. We lack that, so this is automatically false. For a true-false question, I'm never going to ask you to explain yourself, but just go based off what you know, and then you're on the right track. How about for this one? Is this linear independent or linearly dependent columns? Dependent for sure, right? There's, let's see, 6 columns, but only 4 entries per column. That's automatic dependence. So we'll say here, false again. Now, this one's interesting. Non-trivial solutions. not really a question that maps to this one too well. What are non-trivial solutions all about? Free variables. So my question is, are there free variables here? Yeah, absolutely. They'd be three of them altogether. I don't know what variables because I put the pivots just randomly. But if there are free variables, it is true. There will be non-trivial solutions. I think actually part C is a little bit tricky because we're thinking in terms of theorem 4 on the first one. Well, this one's kind of tricky as well. But I just wanted to add a comment here to say a free variable gives non-trivial solutions. But parts B and C are actually linked together. If we said linear dependent here, it implied non-trivial solutions. So if we say true here, we have to say false here. These are actually linked together. Well, let's take another look. The column space of A spans R4. That's part C of this theorem, but we already detected that part A is false. Everything here is false, so we can just automatically say false right there, since those statements are all logically equivalent. And then finally, the dimension of the null space of A is 3. What would you all say to that? Some say it looks good. Do folks agree? Awesome, I agree as well. The dimension of the null space, let's put down a comment, is equal to the number of free variables. So there's a ton of reminders of just about every single thing we did in linear algebra. Well, it looks like primarily chapter 1 stuff. So that's a good problem to run through. Any questions about any of those conclusions? Okay, well, let's keep on going. Next problem on the list is a linear transformation kind of question. Notice this one is on exam. The exam 2, I almost said, not quite what I meant. This question is on the final exam in spring 2022. The fact it appears again as a review question means you should expect something like this. I might not ask the same parts in the same exact way, but something along these lines would come up. Let's take a look at what's going on. T has a domain of R3, a codomain of R2, and those could be questions all on their own. So keep in mind that that's the domain. R2 is the co-domain. And it says here, find the standard matrix A of T. Well, what they did give us was the standard basis. And if you know how T maps the standard basis vectors, then you know the standard matrix. You can just say A equals T of E1, T of E2, T of E3. This is a tricky question because this formula that we just used, I believe this is in section 1.9, but it's one of those ideas that we looked at on week 4 of the class, and we don't always look at those ideas again. But the fact that it's coming back up here means this is definitely an important element of linear algebra. Building that standard matrix, just knowing how the mapping works on the basis is enough. So 1, 5 is our first column, 0, 1 is the second column, -2, 0 for the third column, and we're done. But we should be careful with these kinds of questions. Let me add a little bit more. This matrix is of size 2 by 3. And we also have that T of X is AX. This alone implies the domain is R3 and the codomain is R2. So notice how if it's a 2 by 3, you take the 2 and the 3, swap them, and that's how you get your domain codomain. So that's a helpful device to just keep the values straight. If it's indicated this way, it's very clear what's domain codomain. But if this is all you see on your exam, we do need to know that concept. How can we reconvene and get that if we forget? Just put that A is 2 by 3. So X has to be 3 by 1. And X comes from the domains. That helps say it's got to be R3. Okay, so that was our first problem there. Next, find the image of X, which is that it's a linear combination of the basis vectors under T. When it says image of, what they're asking you to do is this. This is one of the things about linear algebra that is not easy. It has a specialized language, and image of is a common thing people say for transformations when all you're doing is a function evaluation. That's all we're doing. So that's kind of annoying. Sorry about that. They've been using these ideas for hundreds of years, so we're just stuck with it, I guess. So image of X would look like this. T of 3e2 plus e3. Now, what I wouldn't want to do here is add up those basis vectors, that linear combination, because even if I add them up, here's what I'm going to get. 3e2 means I'll have a 3 right here. E3 is negative 2, 0. Or no, E3 is the standard basis for R3. Oh, geez, I would have to actually calculate that. 3e2 would go like this. 0, 1, 0. Plus E3 would be this one, 0, 0, 1. And so that would come out as a 0, 3, 1. So if we try to calculate this way, T of 0, 3, 1, we could get a value out, but now we have to use the matrix multiplication. There is absolutely a faster way on this problem. We should just use linearity. So here's my alternate suggestion. If you use linearity, this breaks up. Not a lot of functions do this, so that's why this is a very special kind of function. You can put in T of E2, excuse me, T of 3 times E2 plus T of E3. Then in linearity, this 3 can be moved out front. So now it's 3 T of E2 plus T of E3. And notice we still haven't had to use a matrix multiplication. Although this works, we already know what T of E2 does. It just maps to 0, 1. So this is 3 times 0, 1. T of E3 maps to negative 2, 0. So altogether, this just turns into a negative 2 by 3. And I think that's a faster way to calculate this thing. You don't have to do a matrix multiplication, so that's always beneficial, I think. Any questions, folks, with the steps so far? Okay, the last questions on here, you could find some help on the notes from right about here. I put in the theorem just how it came from the textbook verbatim, but the main takeaways of this theorem are you have that T maps onto Rm if and only if the columns of A span Rm, which means there's a pivot in every, well, this one would be row for spanning. It's definitely confusing in a way. And the way I try to remember this one because of the confusion is, I think of the onto statement right here as being equivalent to the statement right here. Onto means you will always have a solution, no matter what. But then it relates to spanning and the fact that we have pivot position in every row. So that's how the ideas can connect. Theorem 4 is a pretty interesting theorem. It's more interconnected than we think, because we usually just think of the invertible matrix theorem as the superstar. But this one's in many ways better because it handles more matrices, the non-square ones. So down over here, we want to pivot in every row. This one says T is 1 to 1, if and only if the columns are linearly independent. But that's just a statement of pivot in every column now. Why pivot in every column? Because that eliminates the free variables, and so now we have independence. Pivot in every column. Okay, so that's how the theorem goes. But column of what? It would be the standard matrix A. So we need to take a look at that again. Oh, I thought I could fit this all on one screen. Let me zoom slightly differently. There we go. So back to this question. What would you all say to this one? Is T 1 to 1 or not?
Yep.
But that would mean we've got a on-to mapping for sure. So yeah, I agree. This one, if we do a fast row operation, we'd eliminate the 5, and it looks like the pivots on this would be here and here. So we can say for sure that T is onto, since A has a pivot in every row.
Onto is longer than one, column is longer than row. That's why I remember it.
I like that. Yeah, absolutely. Could you say that again?
Onto is longer than one, column is longer than row.
So onto is longer than 1 and column is,
Longer than row, like word wise.
Gotcha.
It's dumb, but
no, I like that. Any little trick that makes sense is going to help a tremendous amount. So I like those kind of ideas in mnemonics. So here we have 3 columns. That means those columns are automatically linearly dependent, right? But it also means there's no way to get a pivot in every column. It's at most it pivots here and here. So that means for 1-to-1, we will say T is not 1-to-1. If you like the word injective, that's how the French say it. Because, and you have options here. You might just say the columns are linearly dependent for sure. There are more columns and entries per column. Or you might say there is not a pivot in every column. Totally up to you. I'll go with that thing we wrote down there in the theorem. Because there is not a pivot in every column. So that's our transformation kind of problem. Because this is a final exam, and this is the last, or final exam review, and this is the last thing we're doing today, I don't think it's inappropriate to give out hints. But I did give a question pretty similar to this one. Not exactly similar, so you'll want to know some of the ideas we put down in pencil as well. But expect something like this one on the real final. Any other questions, folks, with this problem before we try it next? Okay, let's keep on going down and see what else is going on here. Another linear transformation. And problem number 4, I wrote the exam a few days ago, so I honestly forgot if I asked this question or not. I have no idea, completely honest with you. But I am going to ask a Cramer's rule problem, so we should be ready for that one. This one I'm not sure, so I'll leave it up to the class. Should we give this one a try just to see how it goes? Okay, there's a lot of linear algebra questions on these, so even if we do a problem not on an exam, still it's good for the review. So the transformation goes this way. That's sort of not helpful. So our first goal is really to fix the notation. I would rather call it T of X. X is now equal to X1, X2. This is our standard way of representing these algebraic objects in linear algebra. And instead of writing out this column, go where to the comma is, and write it out this way. 4x1 plus 3x2, and let me try again on that penmanship. Then 2x1 plus 2x2. So this gives us not the matrix we want just yet to answer this question, but it gets us started. And also we can tell that, yeah, x comes from R2, so that's the right domain. The image has 2 entries, so that is the right codomain. Next thing we need to do is, when you look at that, and look at it really carefully, it's really just a matrix times the vector x. Any volunteers for what would go in both of these columns? Exactly. So for 3, 2, 2 does the job. Really, all you're doing, grab here where x1 was, pull the coefficients, and you've got your 4, 2. For x2, it's 3, 2. So we do that quite a lot, but sometimes it's good to just practice it just so we know it's coming. So what we've done is we've written this out as A times x. This is the matrix A, just to be specific. And we're looking for a function, the inverse of the mapping T that was just given. So this is saying it should be an invertible mapping we had here. And we could test that out just by taking the determinant of A right away. So determinant A is 8 minus 6 for a value of 2, which is non-zero, which implies A inverse exists. But the bigger thing we want is if the standard matrix A right here is invertible, that implies immediately the original transformation is also invertible. So let's say here, T inverse exists as well. And in fact, the formula goes like this. T inverse of X is just A inverse times X. But this is where the rest of the instructions kind of take over. This was same as a homework problem we did, which feels like a lifetime ago, a few months ago, way back in the day. It was a little bit colder. Well, we still had to do that same kind of thing. So what it's going to boil down to is we need to actually calculate that inverse. Here's a nice formula for a matrix inversion if it's of size 2 by 2. A inverse equals, take the reciprocal of the determinant, so 1/2 coming from here where we got the determinant to 2. And then it's a weird little game on these entries. With the main diagonal 4 and 2, do we swap it or multiply it by -1? Anyone recall?
Well,
Good call. This is a swap on the main diagonal, so it should be 2, 4. If you memorize where the swap happens on the main diagonal, you'll know this is where the negation happens. So -2, -3. It's being divided by a half, so we could do that right now if we'd like. This will be a 1, -1, -1.5, and a 2. So we're just about done with this problem. I'd say this is a big takeaway on this. Even if I don't ask exercise 4, this is surely something you're going to need to know and do on the exam. There's more than one way to invert a 2 by 2, but this is a very encouraged way. It saves a lot of time. So finally, our answer goes like this. T inverse of x1, x2. We're writing our answer in the same notation the problem was given. If you call that just x, I'm not too picky about that part. But for the other parts, let's put in 1, -1, -1.5, 2, x1, x2. That's not the right notation, but when we multiply, we're putting it in the right notation. We'll take 1 times x1 minus 1.5 times x2. So x1 minus 1.5 x2. Then comma for our second entry, so we're just going sideways now. -1 times x1, so -x1. 2 times x2 for a 2x2. And that's our answer. My work here is all over the place, so let's box it out as well, just so I can convey that's what we were going for. We did it, folks. That's the inverse. Big takeaways are invertible matrix theorem happens right here to determine an inverse exists. And that's a really nice formula for matrix inversions. Well, that's another problem down. Any questions or comments before we try the next? Okay, on to Cramer's rule then. I always get a little bit foggy on Cramer's rule, just how it goes when I'm about a year out from doing this class. It's kind of funny. It's something that is not so bad, but you need practice to keep it in your head. So this is on the real final exam. If you practice on something of this size, then that's all I'm going to ask. I'm not going to ask a 3-variable, 3-equation system. That gets just too long on a real final. That's better for homework. First step in Cramer's rule is you take your system of equations and we must write it as a matrix equation. That's why that was a problem on the first exam 1, writing out matrix equations and vector equations. It just comes all back. So let's transfer this to AX equals B, where A equals, this is not an augmented matrix. We refer to this as a coefficient matrix because we're just grabbing these entries right here. So it'll be a 1, 2, -3, 1. X, well, this part is not as important, but we might as well specify things if we're doing that. The thing that's really important is the vector B. I ran out of horizontal space, so let's put it down below. B is the right-hand side, so it'll be 1, -2. We might as well leave that highlighted. And this is our setup for Cramer's rule. Next thing you want to do is calculate 3 determinants, depending on how you format your answers. I usually like just get the determinants out of the way. So we need determinant of A. This one's going to be the denominator. So let's put this one in blue. That'll be a 1 minus of off-diagonal product would be a -6. So this would be a 7 altogether. Now we know all of our denominators are 7s. Next, we calculate these things. Determinant of A1B. And that's notation we only use for Cramer's rule. That's kind of unfortunate. What it's saying is, go and write out this determinant by taking B and place it into column 1 of where A was. So 1, -2 goes here. But the original column 2 stays right where it was, -3, 1. So now this determinant's pretty fast. It'll be 1 minus a +6, so a -5 altogether. Any questions, folks, with these first 2 determinants? Okay, so if you were anticipating this and it makes sense how this went through, then you're probably on good shape for the next part. Determinant A2B looks like this. This time we keep column 1 just as it was, 1, 2. And the notation is kind of clunky, but it's saying in column 2, place the vector B, so 1, -2 goes here. Now the determinant will give us -2 minus 2 for a value of -4, which means we're basically done, but we still have to give the answers. We'll say, therefore, here's our solution. Because the system came as a system of equations, usually you wouldn't necessarily write out your vector values, but you could. That's a completely acceptable answer. But a lot of times you might format your answer like this. Just say what x1 is and what x2 is. For x1, follow the subscripting. You'll have a numerator of -5, and the denominator will be 7. Next, for x2, the numerator will be -4. The denominator will be 7. Finally, we did it, folks. That's the whole walkthrough on Cramer's rule. And I have to say, why do we care about Cramer's rule? You could row reduce this, get an answer a lot faster than I just did with Cramer's rule. The reason we study Cramer's rule, the reason it comes up a lot in a linear algebra class is it's something that you study in differential equations. It comes up a lot. It can come up in engineering settings. Sometimes it's used as a way to look at a parameter in system. We did an application on that. But also, Cramer's rule is mostly used in an abstract way to show how to solve differential equations. So being familiar with Cramer's rules is something that helps out a whole bunch. So you're not necessarily going to solve a lot of systems, but you might analyze them through Cramer's rule, and you'll certainly do differential equations using this. So it's something that just comes back repeatedly. Any last questions, folks, with getting through this one? Okay, let's keep on running through. Now we have a matrix A. We're looking for a null space. And you should expect something like this absolutely will come up. Even if I don't ask question 7 directly, I kind of forgot, I might have. But even if I didn't, you still need to know how this goes because this is how you get your eigenvalues, eigenvectors. You have to solve these null spaces. This will be a common thing that you'll see on the instructions if I ask this question. And it was something that we did on the homework as well. Our answers will be written as a span. So to determine the null space, first thought you might have is, what is the null space? It is this altogether. Null of A is the solution set. So all vectors x such that 8 times x equals the 0 vector. You don't have to write that down, but having that thought in the back of your mind reminds you, all you're doing is row reduction for a null space. So ax equals the 0 vector has this augmented matrix, 1, -1, 5, -4, 0, 0, 3, -3. We're augmenting with the 0 vector, and so it turns into a row reduction problem. Looks like a fast one. Column or row 1, we can copy in to start. Then take row 1, add it to row 2 to get 0, 1, 0, 0, 0. Let me know if my arithmetic goes sideways. That's a very common thing to happen when you're tired. Now, this is a nice row reduction. Lots of zeros occurred, and you're encouraged to do this on a real final exam. We know we're going to multiply this row by -5, add it to the entry above, replacing this row 1. So let's do it right here, right now. Does that make sense to folks as a shortcut? Okay, you're absolutely encouraged to take any shortcuts in row reduction that you find visually when you're doing your final exam. So no questions asked. If you did this all in one step and there was a lot of row reductions, I'd say that's terrific. I just would convey to me, you learned row reduction really well. There are a lot of tricks when you get going with it. Now we're ready to solve it, so let me bring back the variables. Now for row 1, it'll be a statement that x1 equals -3, x4. But let me put that x4 a little bit more to the right now that I'm looking at this, because x3 is also a free variable. So there's x1. How about for x2? These are sometimes kind of confusing, but if there's nothing there, the whole statement is that x2 is 0. So that's kind of a weird one to look at. Now we're taking a look at the free variables, x3, x4. x3 is itself, and x4 equals x4. For me, I have a really hard time writing down this vector x unless I do this right here. Some people can do it. I guess you've done null spaces about 100 times more than 100 times as much as I have, because I need that structure over here to really see the vector x. X is equal to, take the first free variable x3, and it goes 0, 0, 1, 0 for coefficients, plus x4. This one goes -3, 0, 0, 1, where x3, x4 are in R. I skipped the verb, I'll just say in R. If you look at this really closely though, that's just the span of a set of vectors. That's what we have here on the chalkboard, but if you can't see the chalkboard through Zoom, it says span v1, v2, vp is c1, v1 plus c2, v2 plus cp, vp. I'll shorten this up and just say ci in R, which would mean c1, c2 through cp are real numbers. So that's what the span of vectors look like. So from here, we can just say null A equals the span of those same constant vectors that we produced, 0, 0, 1, 0, and -3, 0, 0, 1. So we did it, folks. We wrote our set as the span of a set of vectors. Any questions at all with those steps so far?
Yeah, really quick. If something like this was to come up on the exam and we didn't do the last step where we set null A equal to span of the two vectors, but we did get to the step prior where it was x equals x3, all that information, would that problem be marked wrong, or would we just lose partial credit on something like that?
That's a really good question. If it was an exam 3 problem, I would probably go like this. Let me convey it this way. Let's say this was just not there, so let's use the FBI redacted pen. If we ended on this step, I would probably take off a point if it was an exam 2 or exam 3 question. But on the final exam, I'm not going to be as rough because really, this is the span of a set of vectors when you really look at it. I mean, we put this down there just to convey that. So on a real final exam, I'm not going to try to nickel and dime people as much. Reason I might have taken a point on exam 3 is just to help out with the final exam, connect the dots. But I probably would give this actual full credit now that you asked about it. But other questions at the moment? Okay, any other questions with getting to that step? Or otherwise? Okay, well, This next one is kind of an interesting question. We want a basis for the column space of A. I think that this question, if it came up with that matrix, is a pretty confusing question. What do we know about the column space of A? Well, it's the span of the columns of A. So let's think and start in those terms. Column space of A is equal to the span of the columns of A. So you could just write down here, column space of A is the span of this vector, and so on down the line. But what we want is a basis. And also notice, there is absolutely a pivot in every single row of this matrix right here. We exhibited that right here when we went down and row reduced it. That means when we go to span the columns of A, it is equal to all of R2. Does that make sense on that equation equality right there? Okay, just to help out, it's this, oh, not that one. It's this concept right up here. So we have a pivot in every single row. There's row 1, row 2 with both pivots. The columns of A span Rn. This would be Rm rather. That would be a R2 in our problem. But the column space of A is the span of the columns. So that's interesting. If they are asking, I guess I should say, if I am asking, this is my question, for a basis of the column space of A, but the column space of A is the entire space R2, I would just give the standard basis because that's a good basis for R2. So let's write out basis for the column space, or basis of the column space of A is this one. 1, 0, 0, 1. If you listed it this way as E1, E2, I'd say that's acceptable since that notation is extremely common for E1 to represent that vector. So that's the basis on this problem. I honestly don't think that this is a good question, if I'm being completely honest with you. It's interesting to resolve, but it wouldn't be the real kind of thing I would do for this thing. If I'm asking for a basis for a column space, I think a better question would have been something like a 4x3 matrix, more rows for something more interesting going on there. But in this problem, that's how it would go down. Any questions, folks, with that part B?
Instead of the we write down, for example, the two columns,
Mhm.
then you also write answer.
Let me think. So if we wrote down this column and this column, or are you meaning these two columns?
Oh, yeah,
I think that would be okay, but we would have to test something out. So a separate basis, let's call this part B. And let's give it a new basis, go 1, -1, 5, -4. But notice I made a choice on just grabbing the very first two. Looks like it's the right choice because it corresponds to the pivots right here. So that means even if we look at the determinant, this should be non-zero. That should be the right basis as well. So let's double check. Here to here is -4. Here to here is -5. So it'll be -4 plus 5. Determinant's a +1. So that is in fact a basis. So just make sure if you go that route, you're grabbing the pivot columns and you're in good shape. Absolutely. Any questions about that so far? Okay, I think that's a great addition to this problem. And I think when I originally wrote this problem, maybe that was my thought that you would go and grab those columns. But if I were to write this as a real final exam question, that kind of statement makes more sense for a taller matrix, more rows than what you saw there. But we got through it in two different ways. I like this approach as well. Well, let's go down. A basis for the row space of A. Well, these questions, I have to be a little bit honest with you. I grabbed them from a review about 2 years ago, and our book got updated. They eliminated all the row space questions from the exercises in an entire chapter. So I'm not going to ask this question right here. But if I were to ask it, this row and this row, not the augmented part, would be the basis. Oh, sorry, folks, I did mix the chat. Oh, good call. So Braxton was saying with your statement right here, Rajab, that is the way he would have solved it as well. I think that's a good call, folks. Any questions, folks, at the moment with that row space? Okay, let's answer it just so that it's been answered, but I won't be asking any row space questions on the real final exam. I try not to ask any on the actual homework itself, but a basis for the row space, this is just for the curious, would be this. And it certainly looks weird. Because it's a row space, I would format it as a row, which is now a 1x4 matrix. 1, 0, 0, 3. They definitely look weird. And then on the second row, 0, 1, 0, 0. So that's kind of nice. Why didn't we do the row space? Well, the reason for that is our author himself cited that when we were in this section, that he wasn't going to actually put any homework questions relative to this theorem, even though it is in the book. And if we actually had good homework questions on this, we might have done more row space problems because it's tied in with the fundamental theorem of subspaces. That's the major reason why row spaces are pretty interesting. But since the author didn't support this with any interesting exercises, we just didn't do any row spaces ourselves throughout the course. But just another reminder, example 8 is a real example or a real problem you should expect on the final exam. Because I said that, should we do one like this right away? Okay. If I was going to do this problem again, I'd probably want to think in these terms right here. Let's see if we can find that problem. It should be somewhere. There it is. I guess I should have followed the highlighting. That should have helped me. So this question right here is guaranteed to be the last question on the final exam. Different numbers is all it's going to happen, but same general setup. That was a screenshot. That's not going away, I get. Oh, it is something that stays there. There we go. So we have two different vectors. When we span them, we create a subspace. So this is a subspace of R4 of dimension 2. And we want to find every single vector that would be orthogonal to this vector space. So we call that the orthogonal complement, W with that perpendicular symbol. To do that, we start by finding a matrix A. So we'll set A equals W1, W2. Next, we can say that W is the span of the columns of A, so W equals the column space of A at this point. Why is that important? Because the fundamental theorem says if you're looking for the orthogonal complement and you can write your vector as a column space, then this is all you need to do. The orthogonal complement goes, got my perpendicular symbol upside down. Let me fix that. I don't even know what that would convey. Probably transpose, which would be wrong. The orthogonal complement is going to be equal to the column space of A complement. So we're on this part of the theorem. But then that's equal to the null space of A transposed. So at this stage, we're back to this matrix A. And we just have to transpose those vectors, find another null space. So this is what the setup would look like. Because we're doing a null space, we should write out A transpose right away. So here's A transposed. We're looking at this. Because we're solving a null space problem, we need to augment with a zero vector. Now we've got the full null space we're working on. So first is equality. W1 is the first column, so this turns into the first row. So 1, -2, -1, 2. And likewise, second column is now the second row, so -4, 1, 0, and 3. And just another pretty similar row reduction like the one we got through. It's all about the setup though. So if you feel like you can understand how we connect the dots of grabbing a matrix, going into the column space of that matrix, and then finally using the fundamental theorem from right here, then you'll be in great shape. Any questions, folks, to that stage? Okay, and here's a really huge mental shortcut. Pretty much, this is all we really did, and everything else is just organizing thoughts, showing how we use the matrix. All we did is transpose those columns and augmented with the zero vector. So that is the huge takeaway or big shortcut to this process. But now we got to do the row reduction. You'll notice that these matrices with 2 rows, sometimes these occur a lot on exams because they're fast with row reductions. It can't be too many steps. First step I'll take is just copy in row 1. Next, multiply it by 4, add to below. We'll get 0. That's -8 plus 1, so -7. -4. 4 here plus 3, so an 11. And then a 0. These vectors don't look super friendly all of a sudden. One good thing about the real final exam is I do try to rig the numbers to come out a little bit better. But let's just suffer through the fractions and see what happens. This was not the nicest problem. Let's keep on going. The reason it's not so nice is at this stage, I am forced to divide by a prime number, 7. So we're going to get 0, 1, 4 sevenths, 11 sevenths. Now, that means I want to think of these in terms of sevenths. This one I'm going to think of as a, let's get a pen going, -14 sevenths, -7 sevenths, 14 sevenths. It's not terrible, it's just tedious, but let's keep on going. Now, I'll get a 1 here. I want to multiply this entry by, let's see, to eliminate that 2, I didn't have too much trouble, so I'm going to think of this still as a 1. Just multiply by 2, add to here, and that would be a 0. For the next ones, I have to keep the same process, so multiply this one by 2, it's 8 sevenths, add to -7 sevenths, and we get positive 1 seventh. Let me know if my numbers go bad. Next, let's remember I multiplied by 2 to add to here. So that's 22 sevenths.
That
Add
is
14
supposed to
sevenths.
be -11 sevenths.
Oh, -11 right here. Oh, thank you for spotting that. That's going to make a huge difference. Appreciate it. Yeah, it looks like I divided through, but forgot to flip the sign on that one. That changes things, but in a good way. That's -22 sevenths. So a 14 sevenths we're looking at, correct me if I'm wrong, I think that's a -8 sevenths. Let me mentally go through that again. That look all right to folks so far? Okay, definitely tedious, but we survived it. Let's keep on going then. So we're looking for a null space, and we're trying to find the W perpendicular, the orthogonal complement. So standard steps at this stage, it goes x1, x2, x3, x4. x1 equals -1/3, -1/7 x3, plus 8 sevenths x4. x2 is -4 sevenths x3, plus 11 sevenths x4. And finally, 3 variables thereafter. x3 equals x3, and x4 equals x4. From here, we pretty much have the orthogonal complement. And if you want to skip a step on the stage, here's what it might look like. We're trying to determine the null space. The whole purpose of that was to get to here. And in fact, we can write down the answer based on what we see. The orthogonal complement would be equal to the span of vectors of the same size as W was generated from. These are in R4. And instead of saying what X is, I'm just going to grab the entries. -1/7, -4 sevenths, 1 and a 0. Next, it's 8 sevenths, 11 sevenths, a 0 and a 1, And that's a pretty good shortcut because, as folks have remarked, writing it out, that's a ways up, writing it out like this right here, and then just coming back to the span, that might feel pretty redundant. If that's redundant to you, then this is probably a really good shortcut that works out. Any questions at all, folks, getting that orthogonal complement?
Yeah, so would it be wrong at all to multiply everything by 7 in that scenario to represent the span?
Not at all. Actually, that's a really good choice. And that's a good call because this is just any linear combination whatsoever. So if you change this by multiplying by 7, you just have a new linear combination of those, and it spans the same exact set. In fact, that's the kind of stuff that we did for eigenvectors, right? Whenever we had a set like this, we mentioned you can make your eigenvectors more convenient. And it's a really, really good idea if this was a problem that had more steps. So if we were doing this for a purpose in a longer context, that would be a required step. This would be the best practice. So let's make that happen here. You could also say your answer is -1, -4, 7, 0, 8, 11, 0, and 7. That's a really cool comment. And that's something that is something we did in eigenvector, eigenvalue land, chapter 5. Other questions or statements so far? Okay, last question is about the dimensions. For a dimension, we do need a basis, and a basis has to span and be linearly independent. But you can test linear independence very, very rapidly if it's just two vectors. What you want to look for is where the zeros are. There's a 0 here and a non-zero. You have automatic linear independence because they're no longer multiples of each other. So we can say here dimension of W is 2. Likewise, this one is automatically linearly independent, but there's an even bigger comment. The whole process of finding a null space and writing it out like this will always produce linearly independent vectors. Even if I had like 3 of them, I would know because I solved a null space, those are independent. So there's 2 of them there, and that means the dimension of the orthogonal complement is also 2, and that's also a check of the problem. If this is of dimension 4, because we're in R4, then the reason we call it the orthogonal complement is because it's the subspace that completes the whole right here. That was of dimension 2, leaving 2 other dimensions on the table for the orthogonal complement to take up. So it's as if we took R4, we have split it into planes of 2 dimensions. One plane would look like this, except I can't plot it, it's in R4. And the other plane goes like this. They are completely orthogonal to each other. If this was an R3 problem, that's what it would have looked like, except if we were in R3, this one would have been dimension 2, this one would have been dimension 1, and it would look more like this. A plane orthogonal complement would be just a set of vectors that spans through, coming in perpendicularly. So there's geometry behind this. It's just really hard to draw out. And at this stage, we've got about 6 minutes and some change. What would y'all say is the next question you would like to take a look at? We have something that looks like it uses an isomorphism. We also have a nasty determinant. Let me know if anything jumps out at you. You know, we haven't done a matrix inverse of size 3 by 3. That's been a while on that one. How do you folks feel about this one? Okay, let's give it a try. Find the inverse of that thing here. Even though we're not solving all of them, just another reminder, I will go back to this document and solve them. And I hope to have all solutions posted to the Moodle website. That's not the Moodle website, but I'll have them posted to the Moodle website sometime over the weekend. I'll try to get it early so that if you come back here, you'll see the solutions to the rest of them. But if we're finding an inverse and it's of size 3 by 3, you know, there is a formula for it, but it is a horrible formula. The best practice to do this by hand is to row reduce. Take A, this is a huge augment. We're augmenting by the 3 by 3 identity matrix. So it goes 1, 1, -6, -1, 0, 2, 0, -1, 3. Here's the augmenting. 1, 0, 0, 0, 1, 0, 0, 0, 1, And as a final exam question, this is how I sometimes award partial credit to these kinds of problems. I'm more interested in the concept and you knowing the concept. So if you gave me this much, I would say that's anywhere between a third of the whole credit of the problem to maybe as much as a half. I try to give a lot of credit to just knowing that concept. The rest of the credit is execution. So now we've got to get the row reduction through. And the trouble with this row reduction is if A is invertible, then everything here is going to be a 3x3 identity matrix. We're going for row reduced echelon form. So it could be a lot of steps on this one. So 1, -1, 0, 1, 0, 0. Multiply row 1 by -1, add to the row below to get 0, 1, -1, -1, 1, 0. So that's 1 down. Next, multiply by 6 to add to row 3. We'll get 0. That's a -6 plus 2, so a -4. No change, 3 below. We'll get a 6 on this one. And then no changes for the rest. 0, 1. So we're on our way. We need to now pivot off of here. I think we can fit it this way. Let me see. First thing you want to copy down is row 2. 0, 1, -1, -1, 1, 0. Now let's just take row 2, add it to row 1. That will give us a 1, 0, -1, 0, 1, and 0. Next, multiply by 4, add to the row below to get 0, 0. That's going to be next a -4 plus 3, so a -1. Here it's -4 plus 6, so a +2. Then a 4 and a 1. Look all right to folks so far to that step? Okay, let's take a big shortcut just to simplify a little bit of this work. I've tried to get the identity matrix right here, so we need to flip that sign. So it's been flipped, but that means we're really multiplying all of row 3 by -1. So those will be our next entries. That one little shortcut there actually saves a pretty good amount of time, so we don't just write down a 3x6 matrix with just a sign flip as our only change. Let's go 0, 0, 1, -2, -4, -1. Then 0, 1, 1, 0. Column 1, column 2 cannot change at this point. And our sole operation will just be to add row 3 into row 2 and into row 1, replacing them. So this should give us a 0, -3, -3, -1. Row 1 added to row, let me try again. Row 3 added into row 1 will give us a 0, -2, -3, -1. At this stage, our work is not complete. There's still one last thing you have to do. You need to convey where the inverse is. You could write out the whole inverse. -2, -3, -2, -3, -3, -4, -1, -1, -1, and that works out for me. Or you could just go like this if you're strapped for time, like I am. I'm running out of time pretty rapidly. If you indicate it this way, I'm okay with that. But you have to convey some way, somehow, that you know that's the inverse, so that I know that you know as well. I think that's the whole purpose of the final exam. I'm just trying to determine your understanding of linear algebra. So let's suppose you did a problem like this one. Yeah, like this one, and maybe you just got stuck. Something prevented you from going beyond a certain step. You know how you can still get partial credit? Just say, these are the steps I would take. Just actually write it down in pencil. I need to find the eigenvector for this eigenvalue, but I got stuck. Let's say the eigenvector looked like this. Then my answer would have been A equals, maybe that's the one that you did find. Maybe it's 5004, and so on. So anything you put down on paper, even if it's just indicating the formula or saying a theorem that's relevant to the problem, that is partial credit. The best answers are to go all the way down to here for sure. But keep in mind, you might have to save some time and that kind of stuff. And if you got stuck, just verbally say what your steps would have been, and I will give partial credit for that as well. Well, any last questions or comments, folks, before we call it a night? Okay, have a great night, folks. If you're working really hard on the weekend and you have questions, I will be available through email, so don't hesitate to reach out. Our exam is 5:30 to 7:30 on the 30th of April. I might have other people who come in to join us on the exam since they have 8 to 10 PM exams, and I feel bad. So there might be other people, but no worries, they won't bug you. Have a great night, folks, and I'll see you all next week.
Thank you. Have a good night.
Yep, have a good one, folks.
I did have a
You
quick
betcha.
question for you really fast.
Yeah, absolutely.
How many problems is the final exam expected to be?
I'm going for about 14. I believe that's what it came out to.
Oh,
The problems
okay.
are a little bit faster. There's a few that take a bit of row reduction like we saw here, but it's time to be about anywhere between an hour and 15 to an hour and a half to complete. So you'll have built-in time just to check your work.
Okay. And I would assume the 14 problems are have multiple parts like A, B, C, do this, show this step, right?
Some of them are pretty fast actually, but a lot of them do have like, say, a single problem could be something like, geez, that's way up there. Something like this one we did right here, for example, could be one whole problem.
Okay. All right. Well, thank you. Appreciate it.
It's been fun. Take care.
Yeah, we'll see ya. Oh, I guess one final question too.
Sure.
Sorry. I have been just participating in class over Zoom, so I have not received back um, my exam 3
That's
and I
right.
believe exam 2.
I should have emailed your exam too, but I'm gonna go double check my files and make sure that it really went out.
Okay.
But I should have your exam 2 file just as a PDF if I did email it. I have your
Okay.
exam 3 right here, and I'll get those sent to you as soon as I can.
Okay. Alrighty. Well, thank you.
You bet. Thanks for reminding me about that.
Enjoy your weekend.
It's gonna be a busy one, but we'll do our best. You do as well. Hello. Sorry, say again. Oh, yeah. Yeah, I brought my coat to work too. Just, I mean, it was nice, but I was worried about the rain as well.